so that everything is set and the record of the webinar actually really starts. So it should be within a few seconds. I don't know. Okay, apparently it's working. So I start again. Hi, everyone. Good morning. We are really happy to be with you this morning. So actually, we have this webinar, which will be held by Cailabs and SAIT about how we can use a CANUNDA-PULSE Beam Shaper for high precision Fresnel-type mold drilling. I myself, my name is Gwenn Pallier. I'm product line manager at Cailabs, and I'm this morning with Miquel.
Hello, good morning. My name is Miquel Gomez. I work as a laser application researcher at SAIT in Spain in a research center. We are a research center. Okay, thank you.
So we are really happy to be with you this morning. Just as a start, a few logistic points. There is actually a chat on the right, or on the right, I don't know in which sense is my camera, of your screen, where you can ask all your questions. So two type of questions. If it's like anything not working, you can ask your question. We have Clementine with us who is helping on all the software topics. She can help you if you have any issue of sound or whatever. And if you have questions about the presentation itself, you can also ask them, and we will answer all the questions at the end of the session and at the end of both mine and Miquel discussion. So I guess we will start now with our presentation. So here is the agenda for today. So we put some colors so that you understand when I will be talking and when Miquel will be talking. So we will start by discussing what are actually the challenges of projection lighting manufacturing. Then we will quickly explain what is the FemtoLens project, which actually is a project in which we have done this development. I will also describe the solution that we Cailabs have provided for this project. And then I will give the ball to Miquel so that he explain all the work that SAIT is doing and all the results that they have had on that project. And he will also conclude on what are the next steps for this project. So let's start by the challenges of the manufacturing of projection lighting manufacturing. I will be quick on that, but I need to introduce Cailabs as a start so that you know what we are doing. So you have here on the left of your screen a very nice picture of our brand new building. We are very happy that we moved there in August. So now it's way bigger. We have a lot of space and everybody is in the same building so that we can actually do what is our job, which is actually developing. So it means that we are doing a lot of R&D to really develop new systems. We are also manufacturing the system in Rennes, in our facility that you can see just there. And we are selling, because we are actually a privately owned company, beam shaping systems. So this is really what we are doing, creating the system, manufacturing them, and selling to the market. The company has been founded actually nearly 10 years ago now, based on a unique technology which is called MPLC for multiplane light conversion. This has been developed by our CEO during his PhD, and it's patented from the beginning of the company with now 22 patent families. We have a lot of partners all over the world to help us selling, and we do a lot of export sales actually. We have already raised nearly 17 million euro, and there is actually 62 employees in the company. We are hiring a lot, so if you want to work in the most beautiful part of France, which is Brittany in the west of France, don't hesitate to contact us. We have a lot of open positions. So where do we apply that technology to? Well, to everywhere we can. So along the way, we have actually done a lot of telecommunication applications. This is our Aruna, Proteus, and Tilba product lines. So Aruna is to improve telecommunication on local networks. Proteus is to help for the what we call the network of the future. So basically, we are working with a lot of labs. So in that area, we have actually a world record of the highest rate of data within an optical fiber. And we have now the biggest product line in Cailabs, which is Tilba for space communication or laser communication. The idea is to go from radio frequency communication to optical communication in between the ground and satellites. So this is like all the Elon Musk satellites and all that. So actually, we will be improving that a lot, and we have actually a ground station now to do that at Cailabs. We have also all the custom applications, so it's defense application or medical application. But we are here today to discuss the last but not least product line, Canunda. It's my product line to actually improve laser material processing. What is it exactly? Well, all around us, there are objects which are manufactured using a laser at least at one step of their manufacturing process. It can be a plane, it can be a car, it can be a TV, a computer, your cell phone, your watch. All these objects are actually emitting a laser at some point of their manufacturing process. And we want to improve that very one step, either improving the quality, either improving the yield of that step. To do that, we are actually working in two different worlds. The world of macroprocessing, which is the world of high-power CW lasers. We have for that our Canunda HP product line, and we are also working in the world of microprocesses, which is the world of ultra-short pulse lasers. And for that, we have Canunda-PULSE, Canunda-SPLIT, and Canunda-Axican product lines. For all those products, you have standard solution, which you can see on this slide, but we also have customized solutions, which actually is somehow the topic of today's webinar, because it's a customized solution that we have developed for this European project. So basically, there are a lot of applications for macroprocesses and microprocesses. The historical one, laser cutting, laser welding, or the more fancy one like additive manufacturing or composite heating for high power. And it can be also cutting, drilling, welding, texturing for microprocesses as well. When I see that slide, I'm actually pretty happy to say for now some months already that some years ago we had done very few of those applications, and today we can say that we have actually worked on all these applications, and we have demonstrated at Cailabs that beam shaping can improve all those processes. Today we will be focused on one very specific topic. So we are in the microprocesses world, the world of femtosecond lasers, and we will be focused on mold manufacturing, and especially manufacturing metallic mold. So the idea is to manufacture projection lighting. So what it is? Well, basically projection lighting are used for centuries. Initially, it was lighthouse lenses that are there to give the way to boats traveling the world. Currently, there are a lot more than the lighthouse lenses, and it can actually be very, very small lenses that can, for example, be used for just ambient lighting or to project information, for example, on ground or on walls. Those lenses actually have something very specific in their manufacturing, is they have to be small, cheap, and light. So for that reason, they are manufactured in polymer with a very specific process, which is called mold injection. So we would be manufacturing a mold, and then we would inject the polymer many, many, many times in that mold to have many, many lenses at a very high manufacturing rate and at a very cheap cost. The idea of that project is to manufacture even smaller and even lighter lenses by improving the mold itself. So we are working on metallic mold, and we want to have sub-millimeter range actually pattern on the mold, so that we can have a smaller pattern onto the lens that is manufactured in that very small range. So the idea is to improve the quality of the mold while actually keeping a low manufacturing cost of the whole lenses. To do that, we will be using a femtosecond laser and a beam shaping system that is developed by Cailabs. So this has been made possible thanks to Europe, thanks to a Eurostar project that we are very happy to be part of. And then I will be quickly describing what is femtolens. So femtolens is a Eurostar project that is there to actually manufacture polymer injected lens. The idea is to have actually 5 different partners to develop that. So the end user who is actually manufacturing those lenses is Lentec, based in Spain. And they are actually in that project designing the lens that we have to manufacture at the end. So based on the lens design, we have the mold design. And then there is SAIT, which is taking part of that. So SAIT is actually developing the whole process to be able to manufacture that mold. So SAIT then is saying, okay, I have to manufacture that mold. And to do that, I need that shape. This is where Cailabs get involved. So Cailabs, we are designing and developing one very specific beam shaper for that application. Then all this is actually integrated in Belgium at LASEA So LASEA is also a key partner for that project, because all the system will be set in their machine in order to have a machine for LANTech to manufacture all those lenses in the future. How does it look like? Well, actually, it looks like that. There will be a machine. We will do the beam shaping at Cailabs. LASEA is doing the machine. LANTech is actually at the end designing the lens, and SATE is integrating the whole process inside that machine, and is actually also coordinating the project with LANTech. So what actually solution have we provided at Cailabs? I want to start by explaining a little bit about beam shaping. What is beam shaping? Well, basically, beam shaping, there are many ways to shape a beam. There is temporal shaping, there is phase shaping, and most of the time, hello, we can see. Most of the time, actually, Clementine, you look at the question, yes, and you tell me what's wrong. Most of the time, actually, we talk about intensity profile shaping. So it means that you have the input beam that will be actually generally a Gaussian beam, and you want to change its shape. Maybe you want to do a top hat, like a square top hat, to do your process. That's what you want to do. But actually, there are many ways to do it. I will just mention 3 of them. And actually, each way is using different laws of optics. So the classical laws of optics is the Fresnel lens. So we call that in France classical optics. So it's what has been used for centuries to, for example, design a camera. So in that case, you can also do beam shaping using those laws. That's, for example, what you are doing when you are using aspheres. So you are using a specific set of optical laws. You can use other laws, the laws of diffraction. That's what we call actually in France the physical optics. So that's what is being done actually with DOEs. So they use different laws of optics. So at the end, they are doing the shaping in a different way. The last way is the one we will be discussing today, is using the mode propagation of the laser laws. So it's again another set of laws. And this is what is done when you are using an MPLC, multiplane light conversion system. So at the end, what is very important to understand is that because you are using different laws of optics, in all cases, you can have the very same square top hat in your processing planes, but somehow all the photons didn't reach that plane using the same law of optics, so they don't behave similarly, and it means that at the end, the shaping will be very different. For example, the depth of field will be very different, the phase will be different, the behavior, the stability will be also very different. So I will not be focused so much on the differences in between the different systems. We have a webinar just for that, so you can actually contact us and we will redirect you to those webinars comparing the technologies. But it is important to understand that when you are using one system, there are constraints and it is not the same as using another technology. So what is actually MPLC? I have to explain at least what it is, the basic principles of it. So multi-plane light conversion, it means that you have multiple planes, so a lot of planes, one after the other, each of them tuning the phase profile of the beam. In between the different phase planes, you have to have a sufficient propagation to have a Fourier transformation. It is very important because it's the basic of multi-plane light conversion, and that's somehow what makes it different compared to other technology. Along the way, we have realized that it's much more convenient to implement it in a reflective way. So that's what you can see on the right image of your screen. So the light is actually going back and forward, 2 mirrors, one of them being textures, and that's what is the MPLC. Solved? No, you can see me? Okay. So I hope that it's working for everyone. So basically, that's how MPLC works, and there are a few important things. So in the principle of how it works, there is no theoretical intrinsic losses due to the MPLC. Another important point is that actually you can have multiple beam or single beam at the input and multiple beam or single beam at the output. Similarly, output and input can be either fibered, either free space. This gives a lot of possibilities of implementing an MPLC. In our case today, we will have one input, one output, and it will be fully free space. But other options are possible for other applications as well. The fact that it's reflective, it enables us to really handle high power and high energy. And it is very useful when you want to talk about high peak power, which is the case of femtosecond laser, for example. So what have we done actually in that system? Well, the idea is to have a Fresnel lens. So I guess all of you more or less understand what is a Fresnel lens. It's a lens with a lot of grooves, which are generally triangular. And we were having one very big challenge is that we want to really be able to tune that triangular grooves that are made on the mold itself. So how to do that? Basically, there were two ideas initially. One is to have a triangle. If you have a triangle and you are scanning with a triangle, of course, where you are on the larger side of the triangle, you will drill more and you will get deeper into the material. Another option was to have a square path, but with a non-homogeneous intensity profile over the side of the square. And in that case, you have more energy on the right, for example, so you will drill more on the right and you will again drill deeper onto the material. At the end, we have decided that we will go for the triangle shape for one very specific reason is that it's extremely convenient if you want to really tune your groove. The idea actually in that case is that we have the possibility to rotate the triangle thanks to actually some specific optical system that we add to our system. And when you are actually rotating the triangle, you can play around with the groove shape. So if you are scanning with the scanning direction being parallel to one of the sides of the triangle, you will actually have the maximum depth of your groove, which is on one edge of the groove itself. If you are scanning perpendicular to one side of the triangle, you will have your maximum depth, which is in the very center of the groove that you're drilling. And you can have anything in between by rotating slightly the triangle step by step. So you can really play around having your maximum depth wherever you want, wherever you need, depending on the position of the triangle. So this is really very convenient. Then if you want to adjust the depth of the triangle, you can just adjust the number of passes. You can just adjust the scanning speed or the energy that you have in your triangle. But this is all the process tuning, and it will be described by Miguel after my presentation. So I'm reaching my last slide. What actually have we provided? So we have provided to set two different triangles. Why is that? Well, there was a challenge to drill really small details. So we wanted to have a really small triangle. So we have provided a triangle of 500 micron at the output of our system, which actually became 10 micron in the processing plane, so enabling to have very small details. But the thing is that the smaller the triangle, the less sharp it can be. There are laws of optics that we cannot break at Cailabs, and one of them is the diffraction limit. So based on the size of the triangle and the numerical aperture of the whole system, there is a limit in terms of sharpness that we cannot break. So in that case, with a very small triangle of 10 micron, the reachable sharpness was 0.2. 0.2 is actually the length of the transition from maximum to minimum of the triangle over the whole size of the triangle. So we also decided that we want to try something which is sharper so that we can see the impact of that. And we have also provided to set a larger triangle, which is 20 micron in the processing plane. And in that case, we can be really sharper than that. We can have a sharpness of 0.1. So it's twice sharper compared to the other triangle. And I want to insist on the fact that it's actually 17 times sharper compared to a Gaussian beam. So you really have a top hat which is very sharp in order to have the best details possible on your mold. Another point to mention is that the larger the shape, the larger the depth of field as well. This is also a law of optics that we cannot break at Cailabs, and it is also very convenient to have a larger depth of field. So there was a high interest in testing two different shapes. So we have provided those two systems to say it so that they can play around with the different triangles. And that's it for what we have provided to say it. So I will give the ball to Miguel. You can connect Miguel now so that you can describe the process results and your company. Thank you,
Oh,
Miguel.
thank you very much. So I don't know if I can control the presentation myself. Yes. So first of all, I'm going to introduce THEIT. THEIT is a research and technological center located in San Sebastian in the north of Spain. We have three sites: the main headquarters that is near the university, where it was created by some professors of the engineering university 40 years ago. Then we have another site in the technological park of Miramon, where all the IT and also our laser precision group is located. And we also have a powder atomization facility for doing experimental batches for additive manufacturing. Okay. So this is the structure of the aid. We have 3 vertical divisions dedicated to different sectors, and 1 transversal division, the IT division, that gives support to all the other divisions. So the core of the aid and where it was started was in the materials and manufacturing division. That is the biggest one. Okay. So only this division, we are more than 100 people working. And inside that, we are part of the Advanced Powder Metallurgy and Laser Manufacturing Division. That is the biggest one, as a matter of fact. We are 50-something people. And inside that, our research line consists of 12 or 13 researchers now at the moment. And we work mainly with femtosecond lasers, okay? What are normally the femtosecond lasers used for? Maybe most of you or some of you know it, but just in case, I'm going to explain briefly. Okay, so normally they are used or are associated to high resolution and high accuracy processes. So, for example, we can texture an injection mold. In this case, this is an insert for the mold, in which we can create some micro periodic structures. And here it's an example that depending on what's the point of view, you can get different colors in the surface. Okay. We also can do thin film decoating. We have a stack, for example, of 3 layers of a couple of hundreds nanometers each, and we can select what layer can we remove. Okay. Of course, we can do micro machining. That is the topic of today. Okay. And surface functionalization. That is to use these nanostructures together with hierarchical microstructures to, for example, to make some surface go from hydrophilic to hydrophobic or to oleophobic. Okay. So what's the motivation of this work? Well, Gwenn has already introduced it, but mainly the main idea is that most, if not all, of the industrial or standard laser systems work with Gaussian beams due to its to the fact that it is more easy to manipulate the Gaussian beams, to make them smaller with the lens, and so on. So the thing is that yes, you can go quite small with a Gaussian beam, do smaller and smaller features, but the thing is that the shape that you obtain is a reflection of the profile of the Gaussian beam. So normally the grooves are more or less symmetrical. Okay, so when you want to do like complicated shapes, you can go line by line and try to create the shape by subtraction, layer by layer subtraction with the laser, or you can go to the to beam shaping. Okay, so in this case, well, Cailabs knows more than us about this, but you can do a lot of different shapes with their technology. And in this case, as Gwenn has told us, we went for the triangular shape. Why? Well, because yes, as she said, other shapes were considered, but we went for a triangular shape because as our goal is to manufacture Fresnel UV-shaped, V-shaped grooves in the surface of the insert, we thought that having a triangle and changing the parameters and changing the orientation, we could obtain a whole variety of different grooves. Also, it was important for us to go quite small because we have already obtained triangular grooves, but with that are 150 in size, both in depth and in width, and we wanted to have triangular shapes or triangular grooves that were quite smaller. Okay, so that's what's two of the main reasons to have a beam shaper with a triangular shape. So this is the setup that we have. Mainly on the right hand side, you can see our laser source, that is an amplitude, as a zoom amplitude, and normally we work with it delivering the beam to the left-hand side. You can see here where you have a LASEA standard machining system. What we did for this project is to deviate the laser beam to make it pass through these two modules. Normally, as you have seen before, Cailabs makes everything compact in one mold, but in this case, as we needed two different shapes and it was a prototype, we have these two molds in which in this second one, displacing the module, sorry, to right-hand side and left-hand side, you can obtain these two shapes that she said, okay? After focusing and aligning everything, we take the laser beam to this setup in which we have a precision XYZ stages, okay? And also a microscope objective to focus the beam and a camera to see that we have the shape that we want, okay? In this case, you can see here the triangle. So after analyzing this, we wanted to see or to prove that effectively what we were thinking or we were planning shaping this beam gave the results that we expected. So we did two different type of sets of tests. Okay, the first one is static. We evaluate if the shape replicated on the surface of the mold or that the shape was similar to the beam shape. Okay. Also, what were the ablation characteristics? And then we did, of course, a linear or dynamic test in order to see what kind of routes we could obtain, okay? So in the static process, first, what we did is to find to try to find the focal plane. This we did, okay? We obtained a triangular shape with a side length of 16 micrometers. This is very good because we were using the 20 micron sided triangle, okay? And we did some tests with different number of pulses. So what we saw is that despite increasing the number of pulses, okay, the number of energy transmitted to the surface, the shape more or less remained constant. So this was very good. When looking at it in depth, in volume, we saw, yes, that as we increased the number of pulses, the removed volume was increased, but after one limit, in this case, after 1,000 pulses, we couldn't go any deeper, at least in the static process, because some roughness started to appear, and we thought that some deposition was happening here, okay? So we saw, as I was saying, that up until more or less a number of pulses rounded in 1,000, the effective volume of material removed at the maximum depth increased, and then after that, the process tended to decay a little bit. As Gwenn said, theoretically, the shape of the groove depends on the relative angle between the triangle and moving direction of the beam. So if we displace the beam parallel to one side of the triangle, you should obtain this kind of shape. And if you displace the beam perpendicular to one side of the triangle, you should obtain a symmetrical but a tilted groove, okay? So, well, to explain a little bit more a little bit further this, or why this happens, as you may notice, we have drawn a blue line here perpendicular to the displacement of the laser, and you can understand that the point in the farthest left, we will only see one pulse of the laser when it is displacing, or the minimum amount of pulses, because you only deliver energy when this vertex, left-hand side vertex, is passing through this point. But in the point to the farthest left, right, sorry, of the line, you have the maximum number of pulses that are delivered, because you are delivering energy while all the length of the side of the triangle is passing through that point, okay? So to sum it up, there is a linear dependence of the effective number of pulses radiated on the material, okay? In the axis perpendicular to the displacement. So we did some tests. You see here that the several levels of energy, we did two types of tests. Well, first we set a specific speed that we know that it would work calculating on the fluence that we were delivering to the surface. We set some levels of energy, and what we did is to vary the frequency. So when we were when we increased the frequency, we lowered the power we were using to make sure that the total amount of energy remained constant. So we saw that when we increased the energy, we had deeper grooves, okay? But another interesting thing that we saw also that the shape was more or less as we expected, with much more pronounced tilting in the left-hand side than in the right-hand side. But also what we saw is that even keeping constant the total energy, if we deliver the energy with more pulses of lower peak energy each, we obtain a bigger or larger depth and more effective volume removed. So we saw that the depth and the blade volume depend on the effective number of pulses despite maintaining the total irradiated energy constant. So this was interesting. This is another example to let you see that it's not straightforward to have a triangular beam shape and to do this type of groups, okay? So there's several things that need to be studied when working with it. We also used this module turning or tilting or moving the direction or the orientation of the triangle. So in this case, perpendicular to one side of the triangle. And we obtained similar or nearly identical slopes in the right-hand side and the left-hand side. Right to this point, I have to tell you, or I have to make you aware of one thing. You see that the scale in the y-axis and the z-axis is not the same. So for example, in the first triangle and the upper part, we could guess that there is 30 degrees or nearly 45 degrees, but if you see the actual value is 8 degrees. What I'm saying with this is that from one side, the tilting is not as pronounced as it seems, and also, of course, concurrently, that the roughness is much more smoother than what you feel you can see here, okay? So that's important to make you aware of it, okay? So finally, to sum up, we have proved that, yeah, depending on the orientation of the triangle, we can obtain or very dissimilar or very different, sorry, or very similar tilting of the walls, okay? This is just a preliminary. We need to do more tests, okay? So what are our next steps? Well, we have proved that we can do surface processing with a triangular flat top spot, okay? It's feasible, okay? In static processes, there is a limitation in the effective depth of the micro-machining to maintain a triangular shape at the bottom, so because due to the roughness and redeposition. In dynamic processes, trenches were defined with a precise vortex position and depth, okay? So we could tune or modify how the walls were, who were the walls in terms of tilting. Important thing, a linear dependence on the ablated volume and depth with the pulse number independently or without modifying the total energy delivered to the surface. Of course, we are now doing at the moment, or we want to do further tests with repeated scanning to increase the depth and the width. So if we repeat the scanning in the same place that we were doing the first one, we hope to have a deeper groove and more tilting both in right-hand side and the left-hand side. If we do repetition scans, one scan next to the other, and then in this second place we do 2 scans, we have to have bigger grooves, okay? So we want to see if we can control that in terms of depth and what is the maximum tilting we can have in one wall and in the other. Of course, you can also orientate the triangle not perpendicularly or parallelly to one of the sides, but you can tilt the triangle maybe 45 degrees so you have more parameters there with which you can work with, okay? Of course, other processing strategies will be tested. We will test the burst mode that normally, or depending on how the parameters, or what are the parameters you choose, you go less deep, but you have a much more or a much softer surface in the walls. So this is something that we are planning to do at the moment, okay? So from my side, I think that's all, okay? Thank you very much. And when I give you the floor, okay, to conclude.
Thank you very much, Miguel, for the presentation. Those results are really cool. We are really happy that we have had already all that, and the project is not finished. So there is more coming with our partners in Belgium, Multitel and Lazia. So maybe within 6 months or something like that, we will have a webinar, the whole femtolens team all together. That would be really, really cool. So we are reaching the end of the presentation. So now it's a Q&A session. So actually, there has been a lot of questions on from people who are having problem hearing us, but I haven't seen so many questions technical. Okay, cool, they are coming. So please take your time. Put all the questions that you have. We will read them and try to answer all of them. So question from Johan. Bonjour, Johan. I suppose that it would be possible to synchronize rotation of the triangle according to the circular trajectories required to engrave the lenses. Is it expected some speed limitation to do that? Wow, that's a really cool question. Unfortunately, I guess that for that we will be maybe missing Lazia, but at least I can quickly describe how we do that. So the rotation of the triangle for now is done manually, so it's not live process. The idea was to first test that it's working with a dove prism. So a dove prism is an optical component that is basically rotating shapes. So the next step will be to have that dove prism inside something which is electronically rotating. So we can do that with basic motors and all that. So I would guess that the idea, the speed limitation would be pretty classical speed limitation of such a device that rotate the beams, kind of maybe I would say maybe a Torlabs motor, but probably we can have something better than a Torlab motor, but for the basic ID. So this step is not done yet. As I said, for now it's a manual rotation, and it will be implemented, I hope, in 2023 at ASEA, and we will get back to you when we have a figure for that. And if you want to try it on your side, don't hesitate. We can also try to do it in Saint-Etienne. How does Eurostar's strategy of Fresnel lens manufacturing solve the problem of cost? Thank you. I don't know, Miguel, do you want to answer that one?
Yes. Well, it's not the problem of costs. It's depend if you are able to manufacture a very precise Fresnel lens by replication with injection molding. It should be less expensive than having a glass one that normally it's the only way to have a very precise Fresnel lens. So our idea is to see how far we can go in terms of smallest shape and tilted walls in an injection mold, and how it is replicated to see if we can do it and substitute the glass lenses with the plastic lenses. So that was the main the main reason in terms of costs. Okay, technically it's more the minimum size and shape we can get. Okay.
Okay, so thank you, Miguel. If you have other question, you can write them. I think it's for now the last one, so I give you some more seconds if anyone want to write one more question. Actually, the thing that with the webinar tool, we can see that someone is writing a question, so I want to wait for that question. Okay, another one from Johan. Cool, thank you, Johan, for being there. Will there be an issue of frosting the surface after processing?
Yeah, that's a good question. As a matter of fact, the first test we have done, we were using standard femto-second pulses, okay, and our main idea to move to burst mode is to try to avoid this as much as possible. Of course, even using this process, it is difficult to avoid a bit of roughness, but after some tests we have done in the injection, especially line tech, as we are doing polycarbonate, that is not totally fluid as maybe we could have with polyamide. Normally, if you lower the roughness low enough, the replicated lens doesn't replicate to the nano or roughness. This roughness, it's not an issue in the application for which line tech is using the lenses. Okay, but that's an issue we are working in. Yeah.
Okay, so thank you
Mhm.
very much for the question, Miguel. Actually, I'm very happy we have had that question because I have presented already those results in conference, and we always have that question. So it's pretty cool that we have
Okay.
it also in the webinar.
Okay.
So Johan is thanking us for the answer. I also thank you, Miguel, for being with us
Thank you.
today. Thank you very much for the presentation, for all the work, for everything that we have done already on that very nice project. I
Mhm.
guess it will be the end of the webinar. So
Mhm.
thank you, everyone,
Thank you.
and see you soon. Don't hesitate to contact us if you have any other question. And have a nice day, everybody. Bye bye.
Bye.